All right, so today we're going to start our discussion of comparing two different sample groups and comparing two different populations. So we're going to be looking at two populations, taking samples from each population and then comparing them. All right, let me get this started. So we're going to first look at the different hypotheses tests that we use. Then we'll conduct and interpret hypothesis tests for two population means when we don't know the standard deviation. And if that's the case, your guess is probably that we'd use the student's t, which we do. And then we'll conduct and interpret hypothesis tests for two population proportions. And then last but not least, we'll look at hypothesis tests for matched or paired samples. So when one population is related in some way or another to the second population. All right, so let's say you want to know two groups of breakfast eaten east and west of the Mississippi River. And you can use a technique to decide whether the breakfasts that people eat east and west of the Mississippi River are different. Is one different than the other? All right, so studies often compare two groups. For example, researchers are interested in the effect aspirin has on preventing heart attacks. Over the last few years, newspapers and magazines have reported various aspirin studies involving two groups. Typically, one group is given aspirin and the other group is given a placebo. Then they study the heart attack rate. There are other situations that deal with comparison of two groups. Studies compare different diet and exercise programs. Politicians compare the proportion of individuals from different income brackets who might vote for them. Students are interested in whether the SAT or the GRE preparatory courses really help raise their scores on the SAT or the GRE. And we've already conducted hypothesis tests on single means and single proportions. Now we're going to compare two means and two proportions. And the very beginning of this is really complicated. That's why, I was listening to a podcast yesterday about technology and how in the third and fourth grade, children can't do simple arithmetic. And I find that problematic. But I do know these calculations without a calculator are extremely difficult. So I'm glad we have a calculator to do these calculations for us. Am I going to make it to the end of the semester with this, Nectar? Maybe. There we go. Okay, so we're going to expand on the single proportion, single mean test from chapter 9, and we're going to compare two means or two proportions. The procedure is the same, it's just expanded, and the formulas are really, really, really ugly. So to compare two means or two proportions, you're going to work with two groups. They're classified as either independent or matched pairs. And whether they're independent or matched pairs, that you're going to conduct a test differently if they're independent or if they're matched pairs. It's a different kind of test. Independent groups consist of two samples that are independent, that is, sample values selected from one population are not related in any way, shape, or form to sample values selected from the other population. Matched pairs consist of two samples that are dependent. And typically we are interested in what's happening in those dependent groups, like before, after kind of thing. So you'll pretty much know when you want to use matched pairs because you are interested in the difference in the pairs. That doesn't make a whole lot of sense, but it will. The parameters tested using independent groups are either population means or proportions. In this book, we're going to be using the test for independent groups. We're going to use a test for two population means or the test for two population proportions. If we compare a matched pair or paired samples, we're going to look at population proportions. I'm going to stop and say it's a Monday. And I'm going to start over again. If we're looking at matched pairs, we are going to be looking at a hypothesis test on the difference in their means. So you're actually going to look at your sample data and compare the difference of the means. So you're going to be running a hypothesis test on a subtraction, a difference, and not on the actual individual data values. We'll do that on Wednesday. Okay, so what makes it independent? In independent sample, subjects in one group do not provide information about subjects in other groups. Each group contains different subjects and there's no meaningful way to pair them. Independent groups are more common in hypothesis testing. For example, the following experiments use independent samples. A medication trial has a control group and a treatment group that contain different subjects. A study assesses the strength of a part made from different alloys. Each alloy sample contains different parts. Studies that use independent samples estimate between subject effects. These effects are the difference between groups, such as the mean difference. For example, in the medication study, the effect is the mean difference between the treatment and the control groups. The focus is on comparing group properties rather than individuals. The sample size for this type of study is the total number of subjects in all the groups. In dependent samples, subjects in one group do provide information about subjects in other groups. The groups contain either the same set of subjects or different subjects that the analysts have paired meaningfully. Groups are frequently dependent because they contain the same subjects. That's the most common example. However, it's not always the case. Groups with different subjects can be dependent samples if the subjects in one group provide information about the subjects in the other group. For example, statisticians often consider different samples that include pairs of siblings to be dependent because one sibling can provide information about another sibling for some measurements. Other studies use matched pairs. In these studies, the researchers deliberately pair subjects with very similar characteristics. While matched pairs are different people, the statistical analysis treats them as the same person because they are intentionally very similar. For example, the following studies use dependent samples. A training program assessment takes a pre-test and post-test scores from the same group of people. A paint durability study applies different types of paints to portions of the same wooden boards. All paint types are on the same board and they're considered paired. Studies that use dependent samples estimate within subject effects. These effects are the differences between paired subjects, such as the subject's mean change. For example, the training program assessment estimates the mean change for subjects from the pre-test to the post-test. The emphasis is on the difference between paired subjects. The sample size for this type of study is the number of pairs. Terms such as paired, repeated measurements within subject effects, matched pairs, and pre-test, post-test indicate that the groups are dependent. All right, so let's calculate a hypothesis test with two population means with an unknown standard deviation. So we're going to be looking at two independent samples. They are simple random samples from two distinct populations. For the distinct populations, if the sample sizes are small, the distribution that the sample comes from should be normal. If the sample sizes are large, then we don't really care about the underlying distribution of the population. The comparison of two population means is very common. A difference between the two samples depends on both the means and the standard deviations. Very different means can occur by chance if there is great variation among the individual samples, because we happen to know that the mean is calculated using every single data value. So if there's a large extremes in the data values, that is going to affect the mean. In order to account for the variation, we take the difference of the sample means, x bar subscript 1 minus x bar subscript 2. The bar over the top of the x indicates that is a sample mean, and divide by the standard error in order to standardize the difference. The result is a t-score test statistic. And this is how it's calculated. Because we do not know the population standard deviations, we estimate them using the two sample standard deviations from our independent samples. For the hypothesis test, we calculate the estimated standard deviation or standard error of the difference in the sample means x bar sub 1 and x bar sub 2. The standard error is calculated as follows. It's the square root of the standard deviation of the first sample squared divided by its sample size, plus the second group standard deviation squared divided by its sample size. Right? So that is the standard error of the mean for independent samples, comparing two independent samples. So do you want to calculate that every time you have to calculate it? Yeah, that one's not too bad. It gets worse. The test statistic then would be calculated as follows. You're going to take the difference in the sample means and divide it by this standard error of the means for independent samples. Now, typically, we are looking at a hypothesis test that compares the population means, that says that they're the same or they're different, or one is bigger than the other or smaller than the other. So mu subscript 1 minus mu subscript 2 will be 0 when we're comparing these two populations, because we're going to be doing some kind of assumption for the status quo that the means are equivalent. All right. To calculate the degrees of freedom for this test, because a student's T depends on the degrees of freedom, you've got a fairly ugly calculation here for the degrees of freedom, and it doesn't give you an even number. It's going to be a decimal most of the time. So the degrees of freedom for this student's T test is equal to something that's similar to that standard error, where you take the standard deviation of the sample squared divided by its sample size, and then you add those together and you square that, and then you divide by this calculation down here. And yes, we are going to do this once. Okay, they talk about pooled variance, and then I don't think you have any problems where you pool the variance. When we get to using the calculator to calculate the p-value, when they do that calculation, they do give you the pooled variance. They actually give you the value for it. So your calculator can calculate this for you. I said, I don't think there are any homework problems where you have to pool the variance. But if you do, the pooled variance, which is the standard deviation squared, that's what variance is. You can see the formula there, where N and M are the sample sizes for the two samples, and S sub 1 and S sub 2 are the standard deviations for the two samples. And you do this typically if you think the two populations have the same standard deviation, the same variance. You can pool the variances if you want to. Like I said, I don't think we have any problems that do that. And when can you use a pooled variance? When the ratio of the two standard deviations is very close to 1. All right, let's do our first hypothesis test. The average amount of time boys and girls aged 7 to 11 spend playing sport each day is believed to be the same. A study is done and data are collected, resulting in the data in this table. Each population has a normal distribution. Is there a difference in the mean amount of time boys and girls aged 7 to 11 play sport each day? Test at a 5% level of significance. So what do we have here? We have a sample size of girls of 9. Their average number of hours playing sport per day was 2, with a standard deviation of 0.866. For the boys, we have a sample size of 16. They're playing sport 3.2 hours per day with a standard deviation of 1. Is there a difference in these two samples? So we're not looking as one higher than the other, one lower than the other. Are they different? Okay, so what would our hypothesis test be? Population standard deviations not known, correct? And we're going to let G represent girls and B represent boys. So what are we trying to test here? We're trying to test if these two averages are different or not. So we want to know, is the mean of the group of girls, the population of girls, different than the mean hours that boys play? Are they different? So the null hypothesis would be what? The same? Now, there is another way you could write this. You can write this is that the difference in the two means is 0. There is no difference, or that the mean difference is not equal to 0. Either way, this is going to be a two-tailed test. Would you agree? It's two-tailed because we have not equal to as our alternative hypothesis. So that makes this two-tailed. So when we calculate the value of t and find the area under the curve, half of the p-value will be in each tail. Okay, so we've got our hypothesis test set up. now it's time to start doing some calculations. The first thing we're going to calculate is our t-score, because we need our t-score to find the area under the curve that corresponds to that t-score. And the formula was what? The difference in the sample means minus the difference in the population means, which we are assuming is 0, correct? Divided by what are we dividing this by? The square root of the standard deviation of the boys squared divided by the sample size plus the standard deviation of the girls squared divided by the sample size. Okay, so this was equal to the average for the boys was what, 3.2 hours per day. The average for the girls was 2, is that correct? Minus 0, we're assuming that the means of the boys and the girls are the same. Divided by, we're going to take the standard deviation of the boys, which was 1. We're going to square that, divide that by their sample size, which is 16. We're going to take the standard deviation of the sample of the girls, which was 866 squared, and we're going to divide that by 9. Okay. And that's a 1 squared, not a 12. All right, so let's go hop over to our calculator. And I'm going to use my fraction button, makes things a little bit easier for me to keep track of. So I'm going to go alpha y equals number 1. In the numerator, I'm going to put that difference, 3.2 minus 2. And in that denominator, I'm going to do a square root, second square root. And then I can just type this in. It should work out fairly well. 1 squared, I happen to know is 1. So I'm just going to take 1 divided by 16. And then what am I doing? Am I adding 0.866 squared divided by, what are we dividing by? 9. And I get 3.1424. So my t-score is 3.1424. So we're going to go back to our slide. So t is approximately 3.1424. So this is a two-tailed test. So let me draw a picture. So we have half the p-value. This is half the p-value. 1/2 the p-value is to the right of that t-score, 3.1424. So our p-value is 2 times, since half of the p-value is to the right of the t-score 3.1424, our p-value is twice what? I should probably write this where I have a little more room. The p-value then is 2 times the t-CDF So finding the area under the curve using the student's t-distribution, we're starting at what? 3.1424. We're going to infinity with a mean of, oh, excuse me, I don't need a mean. I need, oh dang, I need a degrees of freedom. So guess what? I get to pull out the other ugly calculation, which is the calculation for the degrees of freedom. Okay, so the degrees of freedom calculation is as follows. You take the standard deviation of the boys, you square that, you divide it by their sample size. You take the standard deviation of the girl sample, you square that, you divide that by the sample size, You take all of that and you square it. And then you divide that by 1 minus n sub b minus 1 times s sub b squared over n sub b. Then you square that plus 1 over the sample size of the girls minus 1 times s sub g squared over n sub g, and you take all that and you square it. So this is going to be 1, because the standard deviation of the boys was 1. 1 over 16 plus the standard deviation of the girls was what? 0.866? 0.866 squared over their sample size was 9. Then you're going to take all that and you're going to square it. You're going to divide that by 1 over 15 because we have the size of the boys group minus 1 times. We're going to take the 1 squared again and divide that by 16, and we're going to square that, plus 1 over 8, because the girls group had a sample size of 9, times what? 0.866 squared over 9, and you're going to square that. And you hope and you pray that you do this right the first time, which I didn't when I was doing this again. The answer is 18 point something. So let's see if we can't go do this on the calculator. Now I'm going to use the fraction button again. And then I'm going to put that stuff in the numerator. And I really don't need to use fractions again. I have 1 divided by 16, but I need to put this in parentheses because I am going to square this. So I have 1 divided by 16, correct? Plus 0.866 divided by 9, 0.866 squared divided by 9. And my calculator should know that it's going to take the 1, divide it by 16. It's going to take the 0.866, square it, divide it by 9, and then add that result to the 1 over 16. And then it's going to take that result and square it. So it should know to do that from PEMDAS. Okay, so what's in the denominator? In the denominator, we had this I'm going to use my fraction button for. Just helps me keep track of it a little bit better. So in the numerator, in that first one, I had what? 1 times 1 squared squared. So I have 1 times 1 to the 4th. And I'm going to go ahead and put that in there just so you can see what happens here. Because I have 1 times 1 squared squared. And then what did I have in the denominator? I had 15 times 16 squared, correct? 15 times 16 squared. So since I'm squaring the numerator, that standard deviation, I'm squaring it and then squaring it again, it's going to be to the 4th power. Okay, then what are we doing? We're adding to that plus, I'm going to put another fraction in here. And then in the numerator of that fraction, I have 1 times, and I am going to type it in, 1 times 0.866 squared squared. So it's 0.866 to the 4th power. And then we're dividing that by what? 8 times 9 squared? And it should follow somewhat a pattern. So we have 1, and the first one is just the 1 over the degrees of freedom of that particular sample. So it's not really necessary, but I put it in anyway. But the second number should be the standard deviation of your first group to the 4th power. And then you're going to divide that by the degrees of freedom of that group, which is 15. times the sample size squared. Then you're going to add to that the standard deviation of the second group raised to the fourth power, divided by the degrees of freedom of that group times its sample size squared. And we pray that that's 18. Okay, so the degrees of freedom is 18.84659. So that's what I need to put in my TCDF to calculate the area under the curve. Okay. So let me go back a slide. So we're going to put right here in the degrees of freedom, 18.8466. Okay, got to go back to my calculator and do this area under the curve. So we're going to do a TCDF. So to get the p-value, we're going to take 2 and we're going to multiply it times. And we're going to go to our distributions. Our distribution, the TCDF is number 6. The lower limit was, what was that t-score? 3.1424. The upper limit is going to be infinity, 1 second, comma, to get the scientific notation, 99. And the degrees of freedom was what? 18.8466. 0.0054. So the p-value is 0.0054. So now we're going to compare that to the given value for alpha. So our p-value was 0.0054. Is that correct? Okay, what was our stated alpha? 0.05? So what's your conclusion? You reject the null hypothesis. If the p-value is lower, if the p-value is lower than the alpha you selected, you're going to reject the null hypothesis. So you reject the hypothesis that the mean hours of sport per day for girls and boys is the same. The sample data supports the conclusion that the mean difference between boys and girls is not 0. So there is a difference between boys and girls. Okay, so let's say something like that. The sample data support the conclusion that the mean of the population of girls and I'm going to go the whole sport thing, is different than boys. There is a difference. Based on the sample data, there is a difference. Okay, now that I put you through that torture, you know what? You want to know the easy way to do it? Oh my gosh. All right, let's go back to our calculators. Got to do it the complicated way at least once. Stat tests. Do you see anything that looks like that might work for what we just did? Which one? 3? It wasn't a z-test, it was a t-test. So which one do you think it is? Or do we have two samples? Did we do a t-test? Let's go take a look at it. You know, what does it hurt you to look at it, right? I can either use data or statistics. I got statistics, right? I mean, you got data here you're going to put in here in a minute. But we were given the statistics, right? They already calculated this for us. Okay, so what do you think you have to do? Do you have to put the mean of the first group in? What was the mean of the first group? 2, if it's girls. Doesn't matter which one you do, not if you're doing not equal to. What was the standard deviation of the girls? Was it 0.866? And the sample size was what, 9? How about the boys? Was their mean 3.2? Their standard deviation was 1, is that correct? Sample size was 16. Alternative hypothesis was we were looking at whether or not they were different. Are we pooling the statistics, thus pooling the variances? Nope, not going to pool them. Although we could, according to the formula that we had, or the criteria we had for pooling variances, the ratio of the standard deviations is fairly close to 1. So we could if we wanted to, but we're not going to. Are we going to calculate? Is that exactly what we got? Now you'll notice that they give you a t-score of negative 3.14. That's because I did girls first and boys second. If I did boys first and girls second, it would be positive. So the only reason it's negative is because the mean of the girls is lower than the mean of the boys. So it's negative. If it were positive, if I put the boys first. Okay, but the p-value is 0.0054, correct? And the degrees of freedom that I calculated with that ugly calculation and got 18.8466. Is that what I got? All right, don't make your life more difficult than it needs to be. Go ahead and use your calculator to calculate the hypothesis test for 2 sample means. So the instructions for this is on slide 25 in your slide deck in Canvas. And it does suggest we do the calculation again instead of calculating, do a draw. Let's do that. So all we got to do is just go back in there and instead of calculate, hit draw. Oh, and I still have something in my y equals. Here it goes. And it should show me the area and the 2 tails, which you can't even hardly see. It gives you the t value and the p value. And that's this thing right here, right there. That's because I did clear out my y equals. That is an absolute value. All right. Okie dokie. When the sum of the sample sizes is larger than 30, so N1 plus N2 is bigger than 30, you can use the normal distribution to approximate the student's t. But you know, this is one of those things with a calculator or Excel, I don't really need to. Back in the day, tables are few and far between. I can show you a standard normal table. I have one on my computer. They're pretty common, pretty easy to find. What's not easy to find is a t-table. And one of the problems with a t-table is that it depends on the degrees of freedom. The t-score depends on, well, the area under the curve depends on the t-score, but it also depends on the degrees of freedom. So you can have infinite number of combinations of t-scores and degrees of freedom. So finding a table that does that is pretty darn difficult to do. But to find, let me just look this up. To find a standard normal table to use a normal distribution is a lot easier to do. So here is the standard normal distribution table, if it'll open. Boy, for some reason it didn't like. That is not chapter 12 that I wanted. So if you were so inclined, you could use a normal distribution approximation and use a standard normal table. I just wouldn't recommend it. Now I can't even find it. I keep finding the stuff that we're going to be doing in chapter 12. This is what we're going to do. No, this is chapter 12. Here we go. No, this is what we're going to be doing in chapter 12. Oh, well, but you can find them on the internet. You can Google standard normal table and it'll pop right up. What doesn't pop right up is a t-table. So the only way to find a t-score, the area under the curve given a t-score, is to have some kind of web page that you can put the t-score in and the degrees of freedom in, and it will calculate it for you. There aren't really any tables that'll do that for you. Okay, all that explanation just to tell you that with the advent of calculators in Excel, you probably don't need to use the normal distribution to approximate the t-distribution. All right. Let's see if we can't figure out this problem. A study is done by a community group in 2 neighboring colleges to determine which one graduates students with more math classes. College age A samples 11 graduates. Their average is 4 math classes with a standard deviation of 1.5 math classes. College B samples 9 graduates. Their average is 3.5 math classes with a standard deviation of 1 math class. The community group believes that a student who graduates from College A has taken more math classes on the average. Both populations have a normal distribution. Test at a 1% significance level. Answer the following questions. Is this a test of 2 means or 2 proportions? Why is it the test of 2 means?
The average.
You're given the average. That is correct. Are the population standard deviations known or unknown? Don't know them, do you? There's no population standard deviation given to you. You're given standard deviations of samples, but not populations. So which distribution are you going to use? Looking at averages, standard deviation unknown, you're going to use, what's that? T-test. What's the random variable? Well, we didn't really discuss this. The random variable is the difference in the means. So it is X bar sub A minus X bar sub B. So the random variable is since we're looking at 2 distinct populations, it's the difference in those populations. Okay, what are the null and alternative hypotheses? The community group believes that a student who graduates from college A has taken more math classes. So is that the alternative? That college A takes more than college B? So what's the null? That they take less than or equal to, or you could write equals. Because again, this is what you test, correct? You test the alternative. So it's important that you get the alternative correct, that it's greater than. The null hypothesis is not quite as important. Okay, let's conduct the test. Okay, so we have two groups. Let's write down what we know. We're going to be using number 4, a two-sample t-test. So we need to know what to put into the two groups. I'm going to use X sub 1. I'm going to use that as college A. So college A, what? Graduates format with 4. And what's the standard deviation? Was that 1.5? And the sample size was 11. And then the second group, I'm going to do college B, which is 3.5. S sub 1 was 1. S sub 2 was 1. And N sub 2 was, how many did we have in that sample? 9. And I'm interested in where A is greater than B. So I'm going to be running the test on greater than, whereas 1 is bigger than 2. Okay, so let me go to my calculator. Stat tests. Number 4. We had that college A had 4 math classes with a standard deviation of 1.5. And the sample size was 11. College B was 3.5. With a standard deviation of 1. That was convenient. And the sample size was 9. And we're interested in where mu1 is bigger than mu2. That's what we're testing. So highlight greater than and hit enter. We're not going to pool the variances, and we're going to calculate. So your test statistic, in case your problem asks you for it, is 0.8899. The p-value is pretty big, 0.1928. Degrees of freedom is 17.3978. So that p-value 0.1928, we're testing at what, a 1% level of significance? Is that what we're testing at? That's bigger. It's bigger than any alpha we're probably going to choose. So if the p is high, then null must slide. So we're not going to reject the null hypothesis, correct? The sample data did not support the claim that college age A graduates more students with math classes than college B. The sample data doesn't support that. Okay. We failed to reject the null hypothesis. The sample data does not support the claim that the mean of college A is higher than college B. At the 1% level of significance from the sample data, there's not sufficient evidence to conclude that a student who graduates from college A has taken more math classes on the average than a student who graduates from college B. All right, have you got your data ready? Have you already put it in? You're going to put the online data in one list and the classroom data in another list. While you're doing that, I'll read you the problem. A professor at a large community college wanted to determine whether there's a difference in the means of final exam scores between students who took his statistics course online and the students who took the face-to-face statistics class. He believed that the mean of the final exam scores for the online class would be lower than that of the face-to-face class. Was the professor correct? You have randomly selected exam scores from 30 students, and we're going to test this at a 5% level of significance. Okay, is this a test of two means or two proportions? Means. Are the population standard deviations known or unknown? Unknown. So which distribution are you going to use? T-distribution. What's the random variable? Well, the random variable is the difference in the means of the online and the face-to-face. So it would be there we go. X bar of the online minus X bar of the face-to-face, using O for online and F for face-to-face. So what are the null and alternative hypotheses for this particular test? So what is he trying to show? That the online score is lower, correct? On the final than the face-to-face. So I noticed the screen's not doing very well here, so I'm going to write it up here. So the null and the alternative. So he's trying to show that the mean of the online class is less than the mean for the face-to-face. And so what would be the null hypothesis? That they're not, so maybe greater than or equal to. You could also use equals, as we have shown over and over again. It doesn't matter on that null if it's less than or equal to, greater than or equal to, or equals, because you're running the test based on the alternative. Okay, so is this a left-tailed test, right-tailed test, or two-tailed test? Well, what was our alternative again? Our alternative is that the online is less than the face-to-face. So is that left or right? Left. Less than means left. And what's the p-value? So let's go calculate the p-value. I put my data in L1 and L2. So I'm going to go run a 2-sample t-test on my data. So I'm going to go highlight data and hit enter. My first list, my online data was in L1. My class face-to-face classroom data was in L2. The frequency of both of those is 1. There's no frequencies. I didn't get more than one score. That's the same. So I didn't use a frequency list is what I'm trying to say. And I'm testing to see if online is less than face-to-face. So mu1 is less than mu2. I'm not pooling the variances, and I'm going to calculate. Okay, so you see at the top, it's testing whether mu1 is less than mu2. The t-score for this data is negative 3.2271, and the p-value is 0.0011. The degrees of freedom for this test is 51.6122. And then you can see the averages for the two groups. The average for the online group was 73. For the face-to-face group, 85. The standard deviation for the online group was 16.9. The standard deviation for the face-to-face is 11.7. So not only do you see that the average is lower for the online group, their standard deviation was larger, so there was more variance in their scores. So if you looked at the range, you would see that the range was higher. All right, so what do we do with that p-value, 0.001? If the p is low, the null must go. So we're going to reject the null hypothesis, is that correct? So the p-value we calculated, 0.001. 1, since the p-value is less than alpha of we did 0.05, then we are going to reject the null hypothesis. At a 5% level of significance from the sample data, there is sufficient evidence to conclude that online final scores are lower than face-to-face. The sample data supports the conclusion that the online scores are lower than the face-to-face. The professor was correct. We're always correct. The evidence shows that the mean of the final exam scores for the online class is lower than that of the face-to-face class. At the 5% level of significance from the sample data, there is sufficient evidence to conclude that the mean of the final exam scores for the online class is less than the mean of the final exam scores of the face-to-face class. And that is where we are going to stop today. Are there any questions? All right, we will see you on Wednesday, and we'll do matched pairs on Wednesday.